Okay. Now, before we move on to the next set of lectures, there is a small fun stuff that I would like to do with you guys, just for fun. I would like everybody to participate. Now, we have been assuming that expected value is the right number, but is it? Is it? Right. So, let us start playing this. Okay, I do not want to be the professor who encourages their students to play lottery games, but if you were to, would you, is the question. So, there is a lottery 1 which gives you 0 rupees every time. There is a lottery 2 which tosses a fair coin and says, heads I give you 100 rupees, tails you give me 100 rupees. Okay, everybody has to raise one hand. Okay. How many of you will play lottery 1? 1, 2, 5, 6, 7. How many of you will play lottery 2? The whole class. Okay. What is the expected value of lottery 1? What is the expected value of lottery 2? Is in this world of our class, which one looks better, lottery 1 or lottery 2? Lottery 2. How can that happen? What is going on? Now, let me push this a little bit. Lottery 1 always gives you 100 rupees, you can only play it once. It is important to say you can only play it once. You know why, you are smart people. Lottery 1 always gives you 100 rupees, lottery 2 gives you 10,000 rupees with probability 0.01 and 0 with probability 0.99. Expected value of both the cases? Expected value of both the cases? 100. How many of you are going to play lottery 1? Wow, more than half the class. How many of you are going to play lottery 2? Some number like 30 of you, 20 of you. Okay. Now, roles have shifted. It is not like more determinism is better. See what is going on. In the first case, lottery 1 was deterministic, second case right, and also in the second case lottery 1 was deterministic. In the first case you chose the random one, in the second case you chose the deterministic one. Okay. Now, as you can see, which is better, there is more depends in the answer, right, the flip has been shifting. Now, I will push this further. I will say lottery 1 you will get 3000 rupees and lottery 2 you will get 4000 rupees with probability 0.75, but I will take 500 rupees with probability 0.25. Now, who is going to play lottery 2? 4 people. Who is going to play lottery 1? Everybody, right. So, completely shifted. Now, just for the fun of it, let us say lottery 1 gives you 0. And lottery 2 gives you $1,000,000 rupees with probability 0.5 and $1,000,000 rupees takes away $1,000,000 rupees with probability 0.5. Who is going to play lottery 2? Only the French guys, because they are doing conversion, right. Oh, it is only few euros, who cares. Right. You know, I used to do this in dollars when I was teaching in Seattle, and I was teaching a professional master's class. So, this is a class where people are working in Microsoft and this, that and the other, and again I asked this question, who is going to win $1 million or lose $1 million? There was one person who was determined to raise their hand. It's like losing $1 million, who cares? I would possibly gain $1 million, that will increase my, right. What is going on? Okay, this is a good time to figure out what is going on. Yes, so who has a theory? What is going on? First of all, have I proven that expected value is not the right thing? Yes, right. Even though we will work with expected value for the rest of this class, At the back of your mind, you should always remember it is not about expected value in the real world. Okay, so what theory could you give? Yes, Divyanshu, you haven't spoken in a while. It is about the degree of risk you are willing to take, and the risk that Bill Gates takes is going to be at a different level than the risk that I will take, and hopefully is going to be at a different level than the risk you take with your money, not your parents' money. Then it will switch, possibly, right? And how do we operationalize risk then? Okay? And there are many different ways to operationalize risk. One way to operationalize risk is to say, oh, I will just take decision based on the minimum, because minimum is the risk. In some case, a minimum is minus $1 million, in one case the minimum is minus 500, in one case the minimum is 0, but that will not give you a satisfactory solution. If you absolutely had to choose a minimum, you will never want to climb Mount Everest. If you always had to choose a minimum, you will not live in your house because the roof will fall down. You will not drive on the road because somebody will kill you. So, we do not make decisions based on the minimum. You could say it is about variance, you could, and that there is a legitimate way of thinking about it. Those problems become much harder to solve, but yes, it is possible. What is something simpler we could do? Do you have a hint? So, how many of you have taken an economics course? So, people who have taken an economics course should have some idea, at least if you have done some microeconomics. You should have some idea of where am I getting to. There is a very famous law in economics called the law of diminishing returns, that is relevant here. So, a law of diminishing returns says, if you have eaten 2 rotis, then the third roti is less important to you than if you had not eaten any roti and the first roti, right. So, is being compared, and same for money, I guess. But if you had to think about modeling that particular law in our world, what are we saying? If you are following law of diminishing returns, then are you a risk averse agent or a risk prone agent? Okay, that was too fast. So, you will get to the answer to that. So, basically what happens in economics, and often we can use this if we are using a model for decision making over humans, is that we do not work with rewards, we do not work with money, we work with the utility over rewards. So, we define a secondary function called the utility function, which is a function that takes in the money value and gives in some sort of calibrated normalized value called the utility. And if you are a risk averse agent, if I take 100 rupees from you versus if I give you 100 rupees, you will feel more pain in taking away 100 rupees than the joy you will feel by getting 100 rupees. Whereas, if you are a risk prone agent, then I can take 100 rupees from you and you will not feel as much pain as the joy you will feel when you get 100 rupees. And if you are a risk neutral agent, then it will be exactly equal. And by and large, our Indian society is a risk averse society. This is because most of us come from a middle class mindset, and our parents have ingrained into us that how important is earning each paisa, and how careful you have to be with your spending decisions, and so on and so forth. And therefore, the utility of negative money, the magnitude of it is much higher than the utility of same amount of positive money, right. However, different societies look at money very differently, and you will find that different societies have more risk taking abilities sometimes than us, or maybe worse also. So, therefore, instead of doing expected value, people use expected utility as the criteria. So, utility is sort of expected to normalize all this, and then you can take an expectation on top of it. So, this would be the utility function for a risk averse agent, which basically says that as money goes negative, the utility becomes very highly negative. It's sort of going down very fast. right, negative utility is going down very fast. But if you keep giving me more and more money beyond a point, yeah, who cares? If I have made my first million, that is amazing. If I have made my second million, that's very good too. If I am making my third million, good. That would be a utility function for a risk averse agent. And these dashed lines sort of show you that if the x axis is same, then early on the utility is much higher, later the utility continues to diminish. So, this is also following the law of diminishing returns. On the other hand, the utility function for a risk prone agent will look something like this. It will say that the 10th million is much more important than the first million, right, and there may be some situations where people who show risky behavior will probably be following this kind of a utility function. And of course, if you are neither risk averse nor risk prone, you will be risk neutral, and then expected value will be same as expected utility. So, for the rest of the course, we will still work with expected value, but at the back of your mind you have to realize that you may not use pure rewards. You may use another utility function on top of those rewards if you are working in a space where agents can be risk averse or risk prone. But as long as they are risk neutral, this is a good enough model. Any questions on this? All right.